Resurgence and Picard-Lefschetz.
Great, thanks very much. First of all, I'd like to thank the organizers for the opportunity to talk, and it's great to be back in Cambridge. I have really enjoyed the program so far. So today I'm going to be talking about resurgence and Picard-Lefschetz decomposition of two-dimensional Yang mills and a deformation of the theory. And this is based on work with Toshiaki Fujimori of Keio University. And I should also mention Daniele Doragoni, who was very helpful at the beginning of this project. Great. So this is my outline. So first, I'm going to set the scene. I'm going to talk about the questions that we want to answer. And then I'm going to talk about two-dimensional Yang mills. So then I'm going to take a detour into quantum mechanics. We're going to learn some lessons, and then we're going to come back to two-dimensional Yang mills and deform it slightly and talk about Picard-Lefschetz and resurgence in this deformed version of the theory. So first of all, let me set the scene. First, let me talk about a trans series. So the same comments that Marcus made yesterday, all the trans series in this talk will be really quite simple. So if you're a mathematician, sorry about that. But this is the kind of trans series I'm going to look at today. So everything in this talk will look a bit like this. We have some sum over non-perturbative contributions. These each come with some constant sk, which might be the action of some solution, or it might be something else. And attached to each one of these contributions, non-perturbative exponential contributions, we have a perturbative series given like that. And this raises some important questions. I think these are the same questions we saw yesterday. Question one is, can we write all observables in quantum field theories in terms of trans series? The answer is probably yes. But the second two questions are more interesting. Can we always derive the non-perturbative data from the perturbative data using resurgence? And the last question is, can we always associate some saddle, some semi-classical saddle to these exponential terms? And I'm going to make some comments on the last question, but I'm mostly going to talk about the second question. So can we always derive non-perturbative data from perturbative data using resurgence? So this, I'm going to abbreviate this as P equals NP. And the answer is no, obviously. So we saw a bunch of examples of this yesterday, but we've known the answer is no for some time because of supersymmetric theory. So if you consider, for example, n equals 2, 2 theory on a sphere, or n equals 2 on a 2 sphere, n equals 2 on a 3 sphere, n equals 2 on a 4 sphere, all of these have observables that you can compute exactly, and almost always you have truncating perturbative series or series that are asymptotic but are Borel summable. And here's another example. This is the partition function of SU2 Yang mills in 2D on a sphere. That's H is 0 means genus 0 today. And as you see, there are sum over non-perturbative sectors, and we have a series in each sector. In each sector, it's 2 terms, apart from the perturbative sector where it's 1 term. So obviously the answer is no. So that's it. That's my talk. Thank you. That's the end of the question. So this is the bowing emoji from which, living in Japan the last 2 years, I've seen quite a lot of. Obviously there's some more interesting things happening. The question I really want to address is why in some cases we get the weaker version of resurgence and not the stronger version of resurgence. So there are a couple of reasons. There are at least a couple of reasons. I'm only going to talk about 2 today. And I make no claims that these are the only reasons. They're just the 2 reasons that are important today. So the first reason is you might have some non-trivial topology. So this is a heuristic diagram of what we call a resurgence triangle. I think the terminology is due to Gerald and Mithad. So each of these phi kns here, this denotes some non-perturbative term in your trans series or non-perturbative series. And if you have some non-trivial topology, let's just say winding number, just being heuristic for the introduction, then you might have this kind of series. So the bottom number, the n, that might be the winding number. And this top contribution here, this is a 0 winding first contribution in this sector. So that would be your perturbative sector. And you might have something that has 1 winding or -1 winding. This might be an instanton and an anti-instanton. And then you might have something like an instanton, anti-instanton, which has 0 winding again. And the one at the top just means it's the next term down. And so you move down the triangle, the action increases. Yes, this diagram assumes that you can associate saddles to these contributions. As you move down, the action of the saddles increases, and that gives you this triangle. And you can only ever hope to get the stronger version of resurgence in a single column of this triangle. And there are a few ways of seeing this. One way is that if you can associate a theta angle, a topological theta angle, to say the winding number, you never expect to be able to derive information about theta from a resurgence analysis of G, the coupling. And another reason is that if you believe this parallel between Picard-Lefschetz and resurgence theory, you'll never get a contour between a saddle, between 2 saddles that have different topology. You'll never find a smooth contour that connects those saddles. If that doesn't make sense, I'm going to talk about that more in a second. Okay, so this is one reason that you get the weaker version of resurgence. The second reason might be Cheshire cat resurgence. Let me talk about this. This is now quite a well-established phenomena. So it was first seen in this quasi-exact solvable quantum mechanics by Kochak, Schulman, Pashik, Tanizaki, and Mithat. And this has been made more rigorous recently using exact WKB by these guys. But you also see it in GFTs. You see it in n equals 2,2 on a 2 sphere. You see it as n equals 2,2, n equals 2 on a 3 sphere, sorry. And you also see it in mathematical functions as well. So it's not just in physics. You see it in modular graph functions. You see it in iterated Einstein integrals. And if you have any questions about these, you should ask Rudolf, who is at the back, because he can answer your questions about the mathematical functions. But the idea of Cheshire cat resurgence is that in the space of theories that you might consider, there are some points, which you call Cheshire cat points, where there are magic cancellations. Now, part of the purpose of this talk is to explain what the word magic means. But at these points, everything truncates. You don't get an asymptotic perturbative series, or you do, but you can't calculate all the non-perturbative data. But the idea is that for theories that live at these points, you might consider a theory in the neighborhood of this theory, and I'll make that more precise later. And when you consider a theory in the neighborhood of this theory, you might find that you do have the stronger version of resurgence. And then you can consider the theory at the Cheshire cat point as a limit of one of these theories. And if you consider it as a limit, then you can apply the stronger version of resurgence and just take it in the limit.
Do you mean, for example, Bessel functions of half-integer order, which just like
Yes.
could be written?
Yes.
Is that an example?
Yes.
Thank you.
Exactly. Great. Yeah. Thanks. Yeah. So, right. The point is that if you take the Cheshire cat, if you take the Cheshire cat theory just by itself, so the theory at the Cheshire cat point, and you just are given the perturbative series, you're in the dark. You can't see anything about the non-perturbative data. You can't use resurgence to calculate any non-perturbative data. But if you consider a theory in the neighborhood, you can. And we embody this by a picture of a cat. And then if you consider the theory at the Cheshire cat point as a limit, when we move from one of these neighborhoods to the Cheshire cat point, we can still use the stronger version of resurgence as a limit. So you see that the cat is still there. If you don't like the name, you have to blame Mithat and his friends. I don't know if they're online to say who's responsible, but so let me just now make a lightning review of resurgence. This is going to help, but we've seen this several times already, so I'll be quick. So the idea of resurgence is that we have some formal power series that's asymptotic divergent, and we use this Borel transform procedure to get the germ of some analytic function, and then we need to take the Laplace transform of this analytic function. And when we do this to get that to the original function, and when we do this, this might have cuts or poles or something in the plane. And these ambiguities are telling you something about the non-perturbative terms which you needed to add. Right, now, let me also give a lightning review of Picard-Lefschetz theory. So the idea of this is that we take the fields of our theory and we holomorphize them. So we make them complex. And we write that action now as a holomorphic function. There's no canonical way of doing this that I'm aware of, so it's a bit of an art. But once you have a holomorphic action, then you need to find the saddles of that action. So that's the finite action solutions of the Euler-Lagrange equations of motion. And then associated to these saddles, you use the real part of the action to find certain privileged thimbles or contours. They're sometimes called Lefschetz thimbles, or sometimes called J cycles, steepest descent cycles, unstable manifolds. There's lots of names for them. And these thimbles, they have special properties. The imaginary part is constant, and they're monotonically increasing or decreasing depending on whether it's the thimble or the dual thimble. And they typically only connect to one saddle and infinity. At special points, they connect two saddles. And then you write the original contour, which I've called gamma here, of your path integral. You write it in terms of these Lefschetz thimbles, and you weight it by some intersection number. Okay. And there is an equivalence, which is still conjectured, a conjecture in the more general quantum case, but let me just work with it for now. So this is taken from some lecture notes by Gerald and Mitad. So this is a one-dimensional integral, zero-dimensional integral, zero-dimensional QFT. And we're just integrating this function between minus pi and pi by 2. So the original contour is just the real axis between these 2 points. And there are 2 ways of doing it. One, we might calculate a series. We get an asymptotic series. We use our Borel resonation machinery, and we get an ambiguity. And that's telling us that we missed something non-perturbative. And you might also do it using Picard-Lefschetz. And so this is the black dots here are the saddles. The blue and red line are the thimbles. And depending on whether you make your coupling constant slightly imaginary in one way or the other way, you get jumping intersection numbers, and this jump corresponds to this ambiguity. Okay, so this raises a question, which is that at a Cheshire cat point, this ambiguity disappears, but this ambiguity is still here. So what is going on when this ambiguity disappears on this side of this equivalence? Okay, so that brings us to the end of the introduction. So the purpose of the talk, first of all, we want to explore resurgence and Picard-Lefschetz structures of 2D Yang mills. When we get truncating series, we've already seen we have one, but when we get it, is it due to a resurgence triangle, or is it due to Cheshire cat resurgence? And then the third question is, if it's due to Cheshire cat resurgence, what is going on the Picard? What is going on the Picard-Lefschetz side? So we still have jumping intersection numbers, but everything is truncating. So what's going on? Why is there an ambiguity on the one side and not on the other? Okay, so that's the question. So let's talk about 2D Yang mills. Are there any questions about the introduction? Great. Okay, so 2D Yang mills. This is an old theory now. The exact solutions of this theory have been known for a long time now, and you can do it in many ways. So it's a good playground to explore some of these questions. Today, just going to consider the theory on some closed surface. H is going to denote the genus because G is going to denote the coupling. And I'm going to work with gauge group UN or SUN. And it's the standard Yang mills action. And in 2 dimensions, I can write this in this form. I introduce a scalar. And there's lots of reasons why you might want to do this, but I'll just work with it for now. And this has saddles. The saddles are monopoles. They're characterized by a monopole number. You have one monopole number for every Cartan subalgebra element of the gauge group. And these saddles have these actions. And I should say for UN, you can also add a theta term, which I'm basically not going to talk about today. Great. And you can calculate the partition function. I'll just talk about the partition function today. You can do this with some other observables. And let me calculate the partition function 2 different ways. First, I'll just follow these nice lecture notes by Blau and Thompson from '93. They gauge fix to the torus gauge, which means they set the off-diagonal elements of the scalar to be 0. Almost all of the integrals are Gaussian, so you need to regulate these integrals using some sort of mode expansion, which you can do very easily. And the end result is that all of the interesting stuff happens for the constant modes of the scalar fields of their Cartan subalgebra elements. And you get this integral. It's a n-1 dimensional integral for SUN. It's an n-dimensional integral for UN. And each of these, this is dressed with a one loop determinant, which in this context is the same as the Faddeev Popov determinant. So you get an exact answer. I'm writing this out because this determinant is going to be important later. Let me talk about a second way of doing this. You can also do this using Picard-Lefschetz. And this is almost identical. And the reason is because everything is Gaussian. So when things are Gaussian, the original contour is basically identical to the Lefschetz symbol. So the only interesting stuff, I could write out the full saddles and the full cycles or the full Lefschetz symbols for all of the modes, but that would take 3 slides, and it's not very intuitive. Instructive. The only real difference is that the one thing that isn't the same as the original contour is the constant mode of the Cartan subalgebra elements of the scalar. And this is just shifted by this 2 pi I times the monopole number. And you could have actually seen that already if you just completed the square in the top up here. Okay, so the Picard-Lefschetz decomposition of just straight 2D Yang-Mills is very easy. And there's not too much to say. Well, you get a trans series, and as we saw before, it's truncating. So what is the reason? Is the reason because we have some topology, or is the reason because we have a Cheshire cat point? And the answer is the reason is because we have topology. So although we can't associate a theta angle in SUN, we can in UN, we still have monopole numbers. So F here is field space. And this is not controversial. This is just saying that the saddles have associated monopole numbers, which means that we have a resurgence triangle, but it's a little bit empty. So it's just one term in each sector, and there's nothing else in the rest of the columns. So that is the reason we have weak resurgence here, because we have topology. Right. But I claim that there is still Cheshire cat resurgence here. In other words, I claim that there are things in this column which are missing, which we haven't seen yet. And that's going to take us to quantum mechanics. Are there any questions about that part? Yeah. Yes. Yes. In large N, that's exactly right. So there's these papers by Okayama and Sakai. Yeah, everything here is finite N. So things are different in the large N case. Exactly. Yeah. Thank you. Yeah. Great. So let's talk about quantum mechanics. These guys again. Okay, so let us start with a very simple action for quantum mechanics. So we have some boson position coordinates, and we have some fermion degrees of freedom, let's say NF of them. And we start with this action. If NF is 1, this is just standard SUSY quantum mechanics. If NF is not 1, then this is some quasi-exact solvable system. And the first thing we do is we integrate out the fermions. And when we integrate out the fermions, we need to start grading things. So we can write, for example, our partition function as a sum over graded parts of the partition function, which are graded by fermion number. So P here is fermion number. And I can write an effective action for the system with P fermions just by moving the one loop determinant that I get when I integrate out the fermions back into the action. So P is the number of fermions, and then there's a log because I've moved it back into the exponential. And then this is the one loop determinant from integrating out these fermions. Okay, and I write it like this here for reasons we'll see in a moment. But you can then write down what this is, and it's just the integral d tau of respect to this. So you get an effective potential, which is like this. So this is this term here is coming from the one loop determinant when we integrated out the fermions, and it's a quantum correction, which is going to be important. Great. So let me now just specialize. Let me just specialize to double well. So it's very simple quantum mechanics now. This is the superpotential. And just to make things more simple, I'll just work with P as 1. So 1 fermion effective action in the double well. And now I start doing perturbation theory. And I calculate the ground state. And this is the answer. Is 0. No asymptotic divergence series, no series at all. And the answer is wrong because there are complex pions. I should just say something about these complex pions here. If you consider this theory with no fermions, these complex pions aren't here. You have something called saddle critical points at infinity, which is like a instanton and an anti-instanton, and then you separate you make the separation infinite. But these complex pions are only really solutions when you start adding this quantum correction from integrating out the fermions. But they contribute, and the right answer looks something like this. So you need to add this complex pion term to your trans series. And so this is the answer, weak resurgence, so not strong resurgence. And why is it that we have weak resurgence in this case? Well, in this case, it's because we're at a Cheshire cat point. Right. So let's go back to our effective potential. And rather than P is 1, let's use P is 1 plus epsilon. Now, I'm not going to write out any of the details here, but when you have P is 1 plus epsilon, you calculate your energy using your ground state energy using perturbation theory. You get an asymptotic divergence series. You can calculate your non-perturbative data up to a trans series parameter from the perturbative data. And then you can analytically continue epsilon back to 0. And in this way, you keep the stronger version of resurgence if you consider it as a limit. Great. But the point of going to quantum mechanics is this. So all of the magic happened when we included the log of the one loop determinant back in the action. And all of the magic happened when we made this P not integer. So we added this log of a determinant back into the action, and that's going to inspire the deformation, which we make in a moment. So now I want to talk about this work that we are doing with Fujimori. And yes, sorry.
So when you're talking about deforming and taking perturbation theory in epsilon and saying that then you have strong resurgence, but I thought that the resurgence you were looking for was the one that explains somehow a perturbative series with relation to the instantons, which are not instantons in epsilon.
Right.
So
yeah.
Sorry, I'm a bit lost of what the resurgence here is mapping what to what.
The perturbative series is still an H bar. You're just considering a theory where you added an extra term. So the epsilon is just a bookkeeping parameter so that you can move around theories.
Okay, so you don't do perturbation in epsilon. You're just taking
yeah.
epsilon to be fixed, can be small as
yeah.
fixed. Okay.
Yeah, exactly. Thanks.
Yeah, sorry, I just wanted to point out that there is another even simpler deformation that you can make that, in which you add whatever term that you want, You pretend it's classical. Well, actually, it's H bar, and then at the end of the day, you resum, and then you treat it back as classical. In which case, you recover the full. You actually have a perturbative series for the SUSY quantum mechanical model, and actually, you don't even get a trans-series. Everything is there. So I believe that this is yeah, it's an alternative, easy way to get the actual solution for the quantum mechanical model.
Right.
Yeah.
Yeah.
It's a sort of Cheshire cat, but in another way, if you wish.
Right. Right. This is true. And indeed, the deformation that I'm going to talk about for 2D Yang mills is not the only deformation, and there's lots of deformations you can consider. So I'm just going to consider one which looks a lot like the one that we've just considered in quantum mechanics, but there's lots that you could do. Thanks. Yeah. Great. Any more questions? Great. Okay. Right. Let's move on. This will appear on the archive some point in the next few weeks. Great. So the deformation is inspired by this Faddeev pop-off determinant, which I already hinted at. So I just add a delta. Delta is like the epsilon that we saw earlier. So I'm not doing perturbation theory in delta. It's just keeping track of which theory we're talking about. I've written out this determinant on the next slide in full. So it's a little bit grim, but it's really just the Faddeev pop-off determinant. So this is what it looks like. And apart from the constant modes, not much has changed. So most things are still Gaussian, but things have happened for the constant modes of the scalar fields for the Cartan algebra. And it's also interesting to note, if you follow the same method as Blau and Thomson, everything happens exactly the same as before. So this is exactly what we saw before, but now there's this extra term proportional to delta in the exponential. And of course, you can just move this term out of the exponential because it's a log. And the effect is that you shift h. So I now have a way of describing a theory with non-integer genus. And also I have a way of describing a theory on a surface with a different genus in terms of a surface with a different genus. So I could describe, I have a way of writing the partition function for a theory on a torus in terms of the theory on a sphere plus a deformation. Yes, okay. So that's the deformation in full. So everything's okay. And just an aside, this is of course this is very common. So this is what happens every time we start integrating out fields. So if we integrate out the fermions from our field, if we are looking at a sigma model, we can put in some Lagrange multiplier. We can integrate out the other fields. We get a one-loop determinant. We can have an effective action. So this is just very heuristic. We have some fields phi2. If we expand it to quadratic order, we get a one-loop determinant. We write it back in the action, and it's always a quantum deformation. So this is just there's nothing controversial going on here. Great, but we have new saddles. So like with the quantum mechanics case, we got these complex bounds, and we started adding quantum corrections. Well, we get new saddles in 2D Yang mills as well. So I just written out the equations of motion at the top. If you take the external adjoint derivative of the second line and then you sub in the first line, you see that we still have monopole solutions. So all of the saddles are still classified by monopole number. So we're still going to get a resurgence triangle. But now we have two terms in each resurgence triangle because this now just becomes a quadratic equation. Right. So this is what the saddles are. There's now two, and this is the action for these saddles. And one of these is, you see, is basically just the monopole plus some quantum corrections. And the other one is actually got perturbative action. So this is going to show up in the trans series as a perturbative part, plus some quantum corrections. Great. Okay. So now we have a resurgence triangle, which really isn't a triangle anymore. So this is what we have. We have two terms, one in the, sorry, in each column, we have two terms, a perturbative, well, something that I'm going to call a perturbative and something that I'm going to call a non-perturbative. Actually, this reminded me of something we saw yesterday. So when we were first considering this model, we hadn't found the saddles because we hadn't got a concrete deformation. We'd found an effective description. And we thought all of these were the same contribution. So you had this, because in the trans series, they all just add to the same term. They just e to the 0. So when we had this weird phenomena where we could, from what we thought was the perturbative data, we could calculate all of the non-perturbative data. But we couldn't go the other way around. We could only calculate some of it. And the reason, the explanation was because there are actually a bunch of saddles that all have the same action. So I think this is some good evidence that although you don't need to know about the saddles necessarily to use resurgence, it can help you see what's going on from time to time. So from this part, you can't calculate this part over here, but you can calculate this part over here. And that explains some of the weirdness that we were observing. Great, so we have a resurgence triangle now, and within each column, we can do resurgence, but we can also do Picard-Lefschetz. Now, let me then talk about, does anyone have any questions about the definition of the saddles? Okay, yeah.
So I didn't get why you include the log, but actually I could have asked it before. Why you include the log term in the saddle point equation? Namely, in saddle point, we typically have a loopwise expansion in h bar goes to 0. So since this is a one loop term, you should include in the saddle point equation, unless we are doing some other expansion, which is no longer the semi-classical h bar loopwise expansion.
Yeah, that's right. So I'm no longer doing a semi-classical. I'm kind of doing like a semi-classical. So
isn't this a bit then you're mixing up in h bar terms which are of order 1 over h bar and h bar to the 0, and then at the end we don't really. I mean, aren't you afraid that then the interpretation is a bit more complicated?
Well, here I can do everything exactly. So I'm not afraid in this situation. More generally, I mean, this is also what happened in quantum mechanics. So I'm also taking my cue there.
Yeah, indeed. But the question would have been also for the quantum mechanics. Yes.
Right, yeah. Let me think about it. Because we can calculate everything exactly in this case, I think it doesn't make, it's not going to change anything I'd say now, but let me think about it. Yeah. Okay, any other questions? Okay. How are we doing? Time. Great. Okay, so this is so first of all, I just want to make a change of coordinates. So the definition I've included has this branch cut now. I've now introduced branch cuts into the action. So I'm just going to make this change of coordinates for the constant, just for the constant modes, just so that I don't have to worry about the path integral measure. What I really want to do by making this change of coordinates is the action with the deformation now lives on this infinite set of sheets because I put a branch cut in, and this is a conformal change of coordinates. So I'm just transforming all of those sheets onto one sheet. So I get rid of the branch cut. The price for getting rid of the branch cut is I now have infinite saddles. So every saddle is replicated on every sheet. This change of coordinates is going to help me deal with that. So C here is an integer, and it's basically telling me which sheet the saddle is on. And the action has become like this. This -1 here has come from the measure. Yes. And interestingly, when we make this change of coordinates, because of the contribution that comes in from the measure, I still get 2 saddles even when delta is 0. So you see, you change coordinates, and the new saddles now survive even when you're considering the Cheshire cat theory. Oh, sorry, I call that Cheshire cat theory. That's a spoiler. When I'm considering a theory with delta is 0. Okay, so you get these 2 saddles, and they're replicated now over infinite sheets. Right, this just says everything I just said. Yeah, okay, so let me move on. This means I now need to talk about a hidden topological angle. So this, I think it was coined by Mithad, but Gerald will correct me. So these saddles, they now have some sort of imaginary part, and this is the imaginary part of the saddle again, plus order G. And when delta is 0, or when delta is any half integer, if I change C to C plus 1, if the saddles on different sheets, the hidden topological angle just differs by a multiple of 2 pi, which means when you exponentiate it in a trans series, they will all have the same action. But it's not the case when delta is some half integer. So the name hidden topological angle comes from, if you have imaginary parts to your actions, this kind of creates some sort of topological grading, because Picard-Lefschetz symbols can only connect 2 saddles that have the same imaginary part. You can't. So basically, this gives you something that looks like a resurgence triangle. It's not actually topological, but that's why it's got this name, hidden topological angle, because it gives this kind of grading by imaginary parts of that action. And so I'm mostly going to talk about SU2 from now on, but for SUN, you actually have n-1 hidden topological angles, and for UN, you have n-1 hidden topological angles and 1 explicit topological angle. And if you don't write the explicit topological angle, then you'll have n hidden topological angles, but you can always put in the theta angle and absorb one of them into the theta angle. Okay, so basically the hidden topological angle you see in this situation is keeping a track of which sheet the saddle you're talking about is on. Okay, so now we can do Picard-Lefschetz decomposition of this. And again, everything is kind of as before. Everything is mostly Gaussian. So I'm just writing, these diagrams are all for the constant mode. I'm just working with SU2 now. So there's only one Cartan subalgebra element. So this is just for the purpose of seeing these things on the plots. So these green circles, these are the things I call the non-perturbed saddles. So these are basically your monopole. So this is just, sorry, this is in one column of the resurgence triangle. So these diagrams are all for monopole number 1, the SU2. But you have an infinite number of them now because we've changed coordinates and moved a bunch of sheets onto one sheet. And then these red crosses are what I call the perturbed saddles, again for monopole number 1. And the bold lines, those are the Lefschetz symbols. The dashed lines, those are the dual Lefschetz symbols. The blue line, that is the original contour. And what else have I missed? The purple ones, they're the ones that connect to the non-perturbative, and the green ones connect to the perturbative saddles. So you can see you get Stokes Phenomena. Oh, so these diagrams, these are all for modulus of the absolute value of the coupling constant is 0.1. The deformation parameter delta is 0.1. Monopole number 1. Okay, so and this is argument of G slightly positive, argument of G slightly negative, argument of G 0. And you see you get Stokes phenomena. So here you get saddles connected by a Lefschetz symbol. And then here and here, the intersection numbers of jumps. So on this picture, I have to include this saddle here with intersection number 1, and this saddle here with 1, and this saddle here with -1. And then here, I drop this saddle, so I get this saddle instead. This is 0, intersection number 1, and then the perturbative ones are the same. So you get a jump. Actually, there's another thing that's worth commenting on here, is that when you deform the theory, these two saddles, they now have different hidden topological angles. So it's not just adding a multiple of 2 pi. And because this extra term is order G, this actually shows up in the trans series as a, this might be referring to what you're talking about. It looks like it's part of the trans series parameter. So it's actually part of the saddle, but it looks like it's part of the trans series parameter. So sometimes people talk about non-integer trans series parameters. This actually shows up here, not because the intersection numbers are non-integer, but because there's a order G part of your saddle, which then comes out of the log and just out of the exponential and looks like it's contributing to the trans series parameter, and it jumps as we move between which sheet we include the saddle from. Okay, this is almost the same picture, but now for monopole number -1. In this case, you see we have to include the non-perturbative saddle on both sides. And we have Stokes Phenomena again in the middle. And the perturbative saddle here has intersection number 1 - 1, so it's 0 on both sides. So even though we get a jump, we never include any of the perturbative contributions. Right, let me just take a slight detour. How am I doing for time? Great. So there is this interesting paper that came out last year by Fujimori, Honda, Kamata, Mitsumi, Sakai, Oda, with a related Picard-Lefschetz decomposition of path integrals to phase transitions. So they have this theorem relating the scattering angle of the collision of n saddles as you pass through a critical point in the coupling, which they call lambda, where the critical value of the coupling is lambda c. And they have this theory that says you can work out the order of the phase transition just by using this formula here and plugging in the number of saddles and the angle that they scatter at. And in this deformed version of the theory, we actually see this in action. So this is, we get a phase transition, which we get once we've deformed the theory. This is the value, the absolute value of the coupling at the phase transition. And this is the value just below and just above. And you see they scatter and at right angles. So you can see this is a second order phase transition. You can see that from the Picard-Lefschetz, which is nice. Okay, you could also do resurgence. So you can now associate a series to each saddle. So this is the series associated to the saddle, which I'm calling the non-perturbative saddle. That's the monopole saddle in the undeformed limit. And this is the perturbative saddle. Yeah.
Can you show the previous slide? Just a question. So in the what you say it's the phase transition, do you have that the perturbative and non-perturbative become the same value?
Yes. Yeah. So at the phase transition, the saddles collide. Yeah. So they go through the same points and then they scatter at some angles. Yeah.
Sorry,
Mm.
pi/2 or 3/2, the angle, how do you
Because if it is pi/2, I would say first order phase transition is 3π/2, second order phase transition. So if I remember the proposal, I just was wondering because
That's a
it
good
looked
question.
like
I'm not sure.
I mean, probably they have a way to see the rotation on them. Okay.
I've not thought about that. Let me ask Toshiaki. I can. That's a good question. Thanks. Right. So, okay. So you can associate a series to each of these saddles, and I now write effective genius is H tilde, and so for delta non-zero or just non-integer, you get asymptotic series, and you can you now have strong resurgence when delta is non-zero. So P equals NP. Everything's factorial divergence. You can calculate everything up to trans-series parameter. Yes, and then you can take the limit where delta goes to 0, or indeed delta goes to any integer. So this is one of the nice things. Is you, if you're working on a sphere with h is 0, and then you take delta goes to 1, you have an effective description of the theory on a torus. And when you look at this effective description, then the cancellation of the saddles, sorry, the truncating of the perturbative series is due to Cheshire cat resurgence. And when you look, if you just look at the theory on the undeformed theory on the torus, then it's due to a resurgence triangle. So you have two different explanations for the same point where you have weak resurgence. Okay, so but now I want to come back to my question that I asked in the introduction, which is here we have an ambiguity, and when delta becomes an integer, everything truncates. And what happens in the Picard-Lefschetz side? So there's this one slide here where I basically just talk about. So these Pockhammers, in the limit where delta becomes an integer, this is going to be the factorial of some negative integer over the factorial of some other vector, sorry, the gamma function of some negative integer over the gamma function of some other negative integer. And you take it as a limit, write it in terms of gamma functions over positive integers. And this is just the example for genus 0 around some monopole background. So this is just in the nth topological sector where n is the monopole number. Okay, so this is now the Picard-Lefschetz decomposition. So n is 1, almost identical before, but now we're at the Cheshire cat point. So this is at the Cheshire cat point, and you see you still have the Stokes phenomena. You still have Stokes phenomena in the at the Cheshire cat point. So there is still some ambiguity in the intersection numbers at this point. But the reason in this case, the reason that this ambiguity doesn't matter and doesn't show up in the trans series when you start expanding is because these contributions are now all equal. So the thimble contribution for each of these saddles is equal. And so even though you have a jump, nothing changes. Okay, so to say that more concretely, you have Cheshire cat points when for different integers c, the hidden topological angle just jumps by a multiple of 2 pi. So that's for 2D Yang wheels on deformed Yang wheels, this is a sort of concrete way of saying where are the Cheshire cat points. Okay. Any questions?
So can you
Yeah.
define what C is? I forgot.
C is just some integer. It's just telling you which sheets you're on. So all of the location of these saddles, they differ by 2 pi IC, and the hidden topological angle jumps as you go one sheet up by 2 pi I 1 plus 2 delta. So if 1 plus 2 delta is an integer, then the contributions on different sheets are identical. And contributions on different sheets that are identical means you lose the jumps, and that means everything truncates. Okay, so that's what's going on in 2D Yang wheels. Okay, so let me make some conclusions. Conclusions is that the quantum corrections from integrating out fields, they are important. So when you start including them in the action, you get new saddles. And you also get your saddles replicated over infinite numbers of Riemann sheets. And when saddles on neighboring Riemann sheets have identical contributions, this can make a difference. Everything can truncate. Okay. Right. Some questions. So these are very broad questions, and I claim to have no answers whatsoever. But one question might be, are these two reasons the only reasons you don't get strong resurgence? That's a very interesting question, I think. So places where you don't have strong resurgence, is it always due to Cheshire cat resurgence, or is it or topological prevention, or are there other reasons? And the second thing is when you start adding these quantum corrections into the action, then you get new saddles that suddenly become genuine saddles in the action. And I would like to know, is this responsible for some of the renewal models we're talking about? I have no idea, but I think it's an interesting question. That's genuine this time. Thanks.
All right, I see a question.
I've got a comment, but before I make the comment, I've got probably a stupid question. Can you show me your slide near the beginning where you showed me that sum over integers? Almost the very, very beginning.
You mean that one? No.
Earlier, right. Yeah, that.
Yeah.
Yeah. Oh, okay. So that's for h equals 0. Okay, because
Yeah.
so that's just a combination of theta functions.
Yes.
Yes, and nothing.
Yeah.
Okay. So just a comment in case it's of interest. This, what you call the Cheshire cat phenomenon, describes very interesting elementary physics, which you might not realize. I mean, for example, if you have a refractive index variation, there are some special ones where there's no reflection from them, reflectionlessness. Now, Chris Howells and I wondered many years ago what's special about the asymptotics of those little potential hills or refractive index variations, where you get, instead of the usual exponentially small reflections, you get 0 reflections. And the answer was kind of curious. It was reflections come from branch points in the complex plane, as we all know, WKB and the like. So what's special about those branch points when you have these reflections and potentials? And the answer is that instead of simple branch points around which locally you have an Airy function, which has all of its asymptotics, which we all know in, we get a little cluster of an odd number, usually 3 transition points. And the local behavior is not an Airy function, Bessel functions of order 1/3, but Bessel function of order 1/2, for which there's no reflection. We call this the asymptotics of reflectionlessness. We call them fake Airy functions because they get. Now, much later, I realized that something similar occurs in a much more interesting context. If you have a little Hamiltonian matrix which evolves states in time dependently, you'll of course get transitions between exponentially small transitions induced by complex degeneracies in the complex time plane. If you have Stokes lines which come from the complex degeneracy, when they cross the real time axis, that's when the transition happens and you get it exponentially small. Well, once again, there are certain Hamiltonians which have this property that there are no transitions at all as they vary. And that's once again because in the complex plane, this degeneracy, which is a branch point, splits. It's a branch point because in the complex plane, the Hamiltonian is non-Hermitian. This is complex. That instead of getting branch points, you get a little cluster of 3, and once again you get this local behavior, which is a half-integer Bessel functions. So the nice physics of this Cheshire cat in quantum mechanics is either reflectionlessness or transitionlessness, and that's been widely applied actually since we wrote about it in various contexts. So just a little comment. I hadn't realized this generality that you've described, but thank you.
Right. Thanks very much. That's interesting. I didn't know.
Other questions? All right, let's thank Philip again. Now there's lunch as usual, but the afternoon is free and the next conference related activity is the formal dinner this evening. Perhaps around 7 in front of Porter's Lodge, some of us can meet, a couple of organizers, so that people can go, so people that don't know where the dinner is, want to go as a group.